Somewhere roughly 56 million light-years from Earth, a spiral galaxy called NGC 1365 has just had its entire life story read back to us, not through a single snapshot, not through a simple measurement of its current size or shape, but through something considerably stranger and more ambitious. Astronomers reconstructed 12 billion years of that galaxy's history, tracing its growth from its earliest formation all the way to the present day, using nothing but the chemical fingerprints left behind in its gas. It's the first time this kind of detailed chemical reconstruction has ever been attempted on a galaxy outside our own, and the team behind it has given this entirely new approach its own name, extragalactic archaeology. This is a real, peer-reviewed discovery, published in the journal Nature Astronomy, led by researchers at the Center for Astrophysics at Harvard and the Smithsonian. And before I go any further, I want to be upfront about something. Despite how this kind of story sometimes gets framed online, this wasn't a NASA mission announcement. It came from astronomers using a ground-based telescope, and giving credit accurately to the people who actually did this work matters, especially for a discovery this genuinely impressive on its own merits. Every quote, figure, and finding in this video comes directly from that published research and the statements of the scientists who actually conducted it. Let's start with the basic idea behind this research, because it's a genuinely clever piece of scientific detective work. Every element heavier than hydrogen and helium, essentially everything astronomers group together under the term metals, gets created inside stars, forged through nuclear fusion over the course of a star's life, and then released back out into the surrounding galaxy when that star eventually dies, whether through a slow, gradual process of stellar winds or a sudden violent supernova explosion. The very first generation of stars ever to form in the universe had almost none of these heavier elements available to them, and built nearly entirely from the pure hydrogen and helium left over from the Big Bang itself. Every subsequent generation of stars forms from gas that's been progressively enriched by everything that came before it, meaning a galaxy's overall chemical makeup effectively serves as a running, cumulative record of everything that galaxy has already experienced. Over billions of years, as generation after generation of stars form, live, and die, a galaxy's overall gas supply gradually becomes enriched with these heavier elements, becoming progressively less pure, less purely hydrogen and helium, and increasingly seeded with the products of countless earlier stellar lifetimes. That gradual enrichment process leaves behind a genuine readable record, provided you know how to interpret it properly. By carefully measuring the relative abundance of specific elements, oxygen in particular, across different regions of a galaxy, astronomers can work backward and reconstruct a surprisingly detailed picture of how that galaxy actually grew and evolved over cosmic time, essentially reading its history the way a geologist might read layers in rock, or the way a biologist might read growth rings in a tree. This general concept, called chemical archaeology or galactic archaeology, has actually been used for years to study our own Milky Way, since we have the enormous advantage of being able to observe stars and gas clouds scattered throughout our own galaxy in extraordinarily fine detail, simply because we're sitting inside it. Applying that same technique to a galaxy 56 million light-years away is an entirely different challenge. Lisa Cooley, the lead author on this research, a Harvard professor and director of the Center for Astrophysics, described the significance of what her team actually managed to accomplish in direct terms, explaining that this represents the first time a chemical archaeology method has ever been used with this level of fine detail outside our own galaxy. That distinction matters enormously. Measuring rough, average chemical properties across an entire distant galaxy is one thing. Resolving those measurements finely enough to actually trace detailed spatial patterns, patterns precise enough to reconstruct a genuine evolutionary history stretching back 12 billion years, requires a level of observational precision that simply hadn't been achieved for any galaxy beyond our own before this study. The research relied on data gathered through something called the Typhoon Survey, conducted using the Irénée Dupont telescope at Las Campanas Observatory in Chile, a facility specifically capable of capturing detailed spectroscopic data across wide areas of nearby galaxies, essentially breaking down the light coming from many different individual regions within NGC 1365 into detailed chemical spectra, rather than simply capturing a single averaged measurement for the galaxy as a whole. Spectroscopy works by splitting incoming light into its component wavelengths, essentially a highly detailed rainbow, and different chemical elements absorb and emit light at very specific, distinctive wavelengths, creating a kind of fingerprint that reveals exactly what elements are present, and in roughly what quantities, within whatever gas that light originally passed through. Applying that technique across many separate regions of a single distant galaxy, rather than just once for the galaxy as a whole, is precisely what allowed this specific study to achieve a level of fine spatial detail no previous extragalactic chemical study had managed before. That kind of spatially resolved data was absolutely essential for this specific research, because a galaxy's chemical enrichment doesn't happen uniformly. Different regions grow, form stars, and accumulate heavier elements at different rates and along different timelines, meaning a single galaxy-wide average would have washed out exactly the kind of fine-grained detail researchers actually needed to reconstruct a genuine, detailed evolutionary history. A galaxy's central bulge, its spiral arms, and its outer disk can all carry meaningfully different chemical signatures, reflecting genuinely different local histories of star formation and gas accumulation, capturing those differences individually, rather than blending them together into one average number, is exactly what let this research team trace out a genuinely detailed, region-by-region evolutionary timeline rather than a single oversimplified summary statistic. Once researchers had that detailed chemical map in hand, they didn't stop at simply describing NGC 1365's current chemical state. They compared their observations directly against sophisticated computer simulations, modeling how galaxies like this one are expected to form and evolve over cosmic time, testing different theoretical scenarios against the actual real chemical patterns observed in the galaxy's gas. Cooley described this specific aspect of the project as a genuinely balanced collaboration between theory and observation, noting that the work was essentially 50% theoretical modeling and 50% direct observation, and that neither half could have produced this result working alone. She went further, suggesting that this particular project offers a genuine model for how observational astronomers and theoretical astrophysicists ought to collaborate going forward, since combining both approaches so closely allowed researchers to reach conclusions that either group, working independently, likely couldn't have reached with anywhere near the same confidence. So what did this combined approach actually reveal about NGC 1365 itself? The galaxy's chemical record, traced carefully across 12 billion years, revealed a detailed growth history, showing how different regions of the galaxy accumulated heavier elements at different rates over time, reflecting variations in star formation activity, gas inflow, and the galaxy's broader evolutionary history across that entire enormous span of cosmic time. That's a genuinely remarkable thing to actually be able to say with real scientific confidence about a single galaxy sitting 56 million light-years away, essentially producing something close to a detailed biography, complete with distinct phases and turning points, built entirely from careful chemical analysis of gas we can only observe indirectly through the light it emits. There's a reason Cooley and her colleagues chose to frame this work around the specific question of our own origins, rather than simply treating it as an interesting technical exercise applied to a distant, unrelated galaxy. Cooley explained the underlying motivation plainly, saying the team wants to understand how we got here, how our own Milky Way actually formed, and how we ended up breathing the specific oxygen we're breathing right now. That's not simply poetic framing. It reflects something genuinely central to why this research matters scientifically. Every atom of oxygen in your lungs at this exact moment was forged inside a star that lived and died long before our solar system ever formed, fused together deep within that star's core and eventually scattered back out into space when the star reached the end of its life, drifting through interstellar space for potentially billions of years before eventually becoming part of the cloud of gas and dust that condensed to form our own sun, our own planet, and eventually every living thing that has ever breathed on it. Understanding exactly how galaxies like our own accumulate and distribute that kind of enriched material over billions of years is directly relevant to understanding the specific chain of events that eventually made a planet like Earth, and life like us, possible in the first place. It's a genuinely humbling thought to sit with, that the specific research technique being described in this video, a chemical analysis applied to gas glowing faintly in a galaxy 56 million light-years away, is fundamentally connected to explaining something as intimate and immediate as the literal air currently in your lungs. Studying that process directly within the Milky Way comes with real limitations too, ones worth understanding, because they explain why looking outward at a separate galaxy entirely actually offers something our own galaxy alone can't provide. We're embedded inside the Milky Way, which gives us extraordinary close-up detail about individual stars and nearby gas clouds, but it also means we're limited to a single vantage point, unable to step back and observe our own galaxy's overall structure and history from any kind of outside, comprehensive perspective. Studying a separate galaxy like NGC 1365, viewed from the outside as a complete whole system, offers researchers a genuinely different, complementary kind of insight, a chance to trace an entire galaxy's chemical evolution as a coherent whole, testing whether the same basic processes believed to have shaped the Milky Way actually hold up when applied rigorously to a separate, independent galactic history. This is precisely why Cooley's team is describing their approach as launching an entirely new field, extragalactic archaeology, rather than simply treating NGC 1365 as an isolated one-off case study. The techniques developed and validated through this specific research, combining spatially resolved chemical mapping with detailed theoretical simulation, are explicitly designed to be applied to additional galaxies going forward, gradually building up a genuinely comparative body of evidence about how different galaxies, shaped by different histories and different environments, actually accumulate their chemical makeup over cosmic time. A single galaxy's reconstructed history is a genuinely impressive achievement on its own. A growing catalog of multiple, independently reconstructed galactic histories, built using the same rigorous method, could eventually offer something considerably more powerful, a real, evidence-based understanding of how much galactic evolution actually varies from one system to the next, and how much of it follows genuinely universal, predictable patterns. It's worth taking a moment to appreciate just how technically demanding this kind of measurement actually is, because it's easy to describe the concept simply while glossing over the sheer difficulty of actually executing it. NGC 1365 sits 56 million light-years away, meaning even its brightest, most active regions appear as extraordinarily faint, compact sources of light by the time that light finally reaches Earth. Extracting detailed, spatially resolved chemical information from a target that distant requires not just a powerful telescope, but an extraordinarily patient, carefully planned observational campaign, gathering enough light across enough individual regions of the galaxy to actually build up statistically reliable chemical measurements, rather than noisy, unreliable guesses. The Typhoon survey was specifically designed with exactly this kind of ambitious, detailed extragalactic mapping in mind, representing years of dedicated observational effort focused on a relatively small number of carefully selected, particularly well-suited target galaxies, of which NGC 1365 turned out to be an especially productive choice. There's also something worth appreciating about NGC 1365 itself as a specific research target, beyond simply being conveniently well-suited to this kind of study. It's classified as a barred spiral galaxy, meaning it features a prominent elongated bar-like structure of stars and gas cutting through its central region, a structural feature believed to play a genuinely significant role in funneling gas toward a galaxy's center, potentially influencing star formation rates and central black hole activity in ways still being actively studied and debated by astronomers. NGC 1365 sits within the Fornax cluster, a substantial grouping of galaxies, and it's actually long been considered one of the most well-studied barred spiral galaxies in the entire southern sky, precisely because its bar structure is so prominent and well-defined, making it an unusually clear, accessible example of a structural feature that appears in a huge number of galaxies across the universe, including some scientists believe our own Milky Way may possess in a more modest form. Galaxies with this kind of barred structure are thought to represent a meaningfully common category throughout the broader universe, meaning insights gained from studying NGC 1365's specific chemical history could plausibly generalize to a genuinely large population of similarly structured galaxies scattered throughout the cosmos, rather than representing some unusual, unrepresentative special case. So here's what I actually want you to take away from all of this. Astronomers have, for the first time, reconstructed the complete 12 billion year chemical history of a galaxy located entirely outside our own now, tracing how NGC 1365 actually grew and evolved across nearly the entire span of the universe's existence, using nothing but careful, patient analysis of the chemical fingerprints preserved in its gas. This wasn't a NASA Space Telescope headline, and it doesn't need to borrow that kind of framing to be genuinely extraordinary. Well, it's a real rigorously conducted piece of research, combining years of dedicated ground-based observation with sophisticated theoretical modeling that has effectively launched an entirely new field of astronomical study, one specifically designed to help answer one of the most fundamental questions we can actually ask about our own existence: how a galaxy like ours accumulates the specific chemical ingredients that eventually make a planet and a species like ours possible in the first place. There's something worth sitting with in how this discovery actually came together, too. It required years of dedicated telescope time, patiently building up the Typhoon survey's detailed spectroscopic dataset, one careful observation at a time, followed by an equally demanding process of theoretical modeling, comparing real observational data against simulated galactic histories until researchers found a combination that genuinely matched what NGC 1365's chemistry was actually showing them. That's not the kind of process that produces a single, dramatic, overnight announcement. It's slow, methodical, collaborative science, exactly the kind of patient work that rarely makes headlines on its own, but that ultimately produces genuinely lasting foundational contributions to how an entire field understands its subject. If you want to know which galaxy researchers study next using this same extragalactic archaeology technique, subscribe, and turn on notifications, because Cooley's team has made clear this is intended as the opening chapter of an ongoing research program, not a single isolated result. And drop a comment telling me whether you think our own Milky Way's chemical history, when eventually reconstructed using techniques like this one, will end up looking similar to NGC 1365's, or whether you think our own galaxy has followed a genuinely unusual distinctive path, because honestly, after seeing how much detail researchers managed to extract from a galaxy 56 million light years away, I think we're a lot closer to actually answering that question than most people realize.